Have you ever had this feeling of accomplishment? You know, this feeling of having done the job right? The feeling that you have when you are happy that you've achieved something. Like, for example, last Friday, you spent the past 2 days writing tests for your code, because we all love writing tests, right? And it's Friday evening, you run your test suite, and you have 100% test that pass. And the cherry on the cake is that you have 100% test coverage. It's a magical moment, you know, when you see that 100% test coverage. So you think everything is good, you are happy, you can go on the weekend very peacefully. And then Monday morning, you arrive at the office, remember this feeling you had on Friday, like you've done other things right. But you open your emails, and you see a lot of bug reports. So, what happened? Did I miss something? Why I had all my tests that passed 100% test coverage, but still there were a lot of bugs? A brief history of tests. So back then, long time ago, when you wanted to test a software, your program, you just had to do it manually. You just compile your program, you run it several times, you tried all the different features. If it works, it's good. But programs became more complex. There are more methods, more classes, more lines of code, more files. And so you couldn't do it anymore by hand. And that's when people came up with these test frameworks, like PyTest for Python, Jest for JavaScript. They made the life of finding bugs, the way of finding bugs more easy, and more efficient. But doesn't mean that you have these kind of tools, doesn't mean that everything is good. So the question we're going to answer today is, does 100% test coverage means all your code has been tested? Does it mean all the edge cases have been tested? Does it mean your code is ready to go on production? Because all these framework tests, they brought this new metric of test coverage or code coverage. And you may think that if I get 100%, it means everything is okay. Because when you get 100% test coverage, it means every line of your code has been executed at least once during the test. And of course, the answer is not necessarily. So hi everyone, my name is Olivier. I'm a developer advocate at AWS, and today I'm very happy to be here with.
Hi everyone, my name is Maha. I am an engineering manager at Elastic. I'm leading a team, the release engineering team. We are offering framework and guidance to the other product team at Elastic to help them to provide and produce their reusable artifacts. I worked as a DevOps engineer before that, and I had a PhD in optimizing performance of multi-tier distributed systems deployed in private cloud. And today, we're gonna talk about mutation testing. How can we benefit from mutation testing? What is it? How can we implement it? So the first question we want to answer, what's mutation testing? What does that mean? Mutation testing is a technique that helps us to evaluate the effectiveness and the efficiency of our test suite beyond the lines of code have been executed. Simply put, I'm testing my test. If you want to explain it shortly, I know that we have a code, we write test suite to test it, and a mutation test is to test the test.
Next step is your mutation test that tests your code, right?
Exactly.
You get it. Next year we come back with another layer.
Don't get afraid. Don't get afraid. We're gonna walk you through all the slide, the presentation, the steps that you need to test your test. Historically speaking, the first time this concept appears was 1971 by a student named Richard Lipton, and the first implementation for the first mutation testing tool was actually a PhD work of a student at Yale University in 1980. So as I said, the main idea behind that is to measure how efficient our test suite today is. It capable to test and cover cover all the edge cases? Are there any bugs hidden? And so on. And that's why we need mutation testing. More precisely, we need that to measure the efficiency, and we need that to improve our tests. Using mutation testing will tell us that there are bugs hidden, there are some edge cases our test suite didn't detect, and those we can improve our test suite. And last but not least, it will help us in pinpointing the time and the root cause of those failures or this inefficiency in our test suite. Now the question, how can we use it? So the idea behind mutation testing, what you need to do, you need to create a modified copy of your program, making only one modification at a time. Then you need to run the relevant tests against that modification, and if the test fails, this is good, meaning that the test detects that there is a change in your program. If the test passes, meaning that the test suite didn't detect that there is a modification in your program, meaning that what you have done hasn't been detected by your test suite. I will simplify. I know it's a lot of information here.
Allow it at this point of the talk that everybody is lost. Like my test fails, then it passes. If my test passes, it fails.
So like what are you talking about? If the test fails, this is good? Yes, this is good, because that means that your test detects that there is a change. So let's break all those concepts to smaller chunks. First of all, what I have said that you create a modified copy of your program. We call this modification or this copy of your program mutant. So the mutant is a modified copy of your original program. Remember, we do only one modification at a time. Let's have a look at this example. So in this example, it's a Python method where I compute the square root of a number. If a number is smaller than 0, I raise an error. Otherwise, I will retain the square root of that number. I will create a mutant of that code. What I will do, before that, the test for that code, actually, it's an assert statement where I say it's the square root of the 49 is 7. If I run this test for that piece of code, the test will pass, everything is good, everything is fine. Now I want to create a mutant. So how I create a mutant? As I said, I will only do one modification at a time. And this modification, I decided to change the operator. So the operator here in the if statement saying if the number smaller than 0, I will change it to make it if the number smaller or equal to 0. So this is a mutant. Then I will run the test again against this modification. And the test actually will pass. And as you can see, that the mutant survived. The result of the test will be survived. Meaning that my test suite didn't detect any modification, which is true. Because in my test, what I tested, actually the square root of 49 is 7. Okay? So the mutant survived, and this is not good. How can I kill this mutant? Because our goal is to kill the mutant. I will add another test statement, a third statement to my test suite saying the square root of the 0 is 0. And then I will rerun the test again. And as you can see, the mutant has been killed by my test. So if I want to summarize it, I made a small modification of the operator by saying if the number smaller or equal to 0, then you continue to do some statements. And in my test suite, I added another assert for checking if I get as an input a 0, that the square root should be 0. And in this case, actually, the test will fail, but at the same time, I will kill the mutant. We're going to see it in more details in the demo.
We have demo.
Yes. So no worries, we're going to walk you through all the details. I've shown you that I made only one change by changing arithmetic operator from smaller to smaller or equal. However, there are hundreds, plenty, tens of types, different types of creating a mutant, and Olivier is going to explain us.
Yes. So I've put it down to 3 different types of mutants, so it's easier. So the smaller mutant we can create is what we call the value mutation. Value mutation is just basically you change the value of like a constant in your code. So like a 0 becomes a 2, a very small number becomes a very big number, a string becomes an empty string. So we just make changes in the values. Another kind of mutation we can do is the decision mutation. Decision mutations are when you change some statements like if, else, switch, and becomes or, these kind of modifications that are done in your code. And the last one is like, yeah, what we call statement mutation. That's when you change the entire function. Like if you have a function, just remove it or just make it empty. We'll see in the demo that you remove the entire content of your function, and that's changing your code. That's a mutation. So just to show you a few of the mutants we can create, this is the arithmetic operators. It means in your code you have a plus b becomes a minus b, times become divided, square becomes modulo, so you have all these changes. We have the array declaration, so we can change the way you declare an array, you can empty an array, add values to it, so these are changes in your code. What we have else? Assignment expression, so plus equal becomes minus equal, all these byte operators even. Block statement, what I showed you, so you have this code, for example, the mutant would be just an empty function, and then you run your test, you see if your test pass or fail. Boolean literal, so false becomes true, true becomes false, not something becomes something. Very basic. And there's a lot of them. You have conditional expressions, equality operator, logical operator, string literals, object literals, optional chaining. Depending on your language, you don't have all of these. Like optional chaining doesn't exist in every language, for example, so it's not always the case. And you have many more. Just want to show you just two more that I like. The method expression. So you have some languages that have built-in functions, like in JavaScript, you have the start with, and the tool you're going to use to do your mutation test may know that and change the method for you. So it becomes end with. The two uppercase becomes two lowercase, and then you run your test and you see if they pass or fail. And the last one, last but not least, the regex one. I mean, writing regex is it's a nightmare for me. Testing them, I don't even do it. And here, the thing is that you have regex in your code, and the mutant will just change the regex to another one. So something I wouldn't do, personally. Okay, so you may think at some point, so what Maha said and what Olivier is saying is that I have my code base, and I have to copy-paste it like hundreds of times and change every statement, every constant, every line of code to create mutants. Nope. Obviously, there are tools for that. Some people thought about it, and there is no one tool fits all for every mutation and every language, but there are tools that automate that for you. So just run the tool, it will create mutants for you. And then, when you run these tools, you have what we call a mutation score. So mutation score, if I put it very easy, it's just the number of mutants killed divided by the total number of mutants. It's not that simple, actually, because you have a lot involved in the exact operation, because you may have some mutant that just time out because you change a while loop that becomes just while true, and it's like it times out at some point. So it's not exactly that, but that's the idea. Basically, same as a test. Like for example, very quickly, we have 4 mutants created, 2 have been killed, 2 survive, so we have 50% test coverage, mutation score, sorry. The goal is to have all the mutants killed, even though Maha will explain to you that it's not always possible to have 100% of your mutant killed, but that's the goal we want to have on our projects. Demo time. I hope you followed, because it's going to be like much more clear with the demo.
Okay, so we prepared for you 2 demos. one in Python. How many of you develop some Python? Okay, that's a great. We have people develop some Python. How many of you develop some JavaScript? Oh, perfect. So we have two demos that almost will cover all the preferences.
It's very basic demo, so everybody will understand in a way.
Yes. So for Python, there are few tools. I'm gonna walk you through them, and we'll have demo about one of them. The first one is MutePy. The installation is really straightforward. Pipe install MutePy, and here we can go to their official web page. There they explain everything about how you install it, how to use it. So it's pretty, as I said, straightforward. The main command is the mute. You run the script file, which is the mute.py, and you pass, of course, your source code, because we need to change it, mute it. And then you pass the unit test, the folder to where your test suite is. And of course, there are other parameters, for example, the -m to show all the kinds of mutants have been created, make it colorful, and you can generate actually the report in HTML or JSON, whatever you like. There are different types you can choose. So I'm gonna go to my PyCharm. Okay, so what I have in my demo, something pretty simple. It's calculator, and I have implemented add, subtract, multiply, divide, and so on. The basic functionality in calculator. I wrote also my unit test for that. As you can see, I have some assert statements for each functionality. I'm gonna run the coverage to see how much coverage I have. So first of all, let me run the test to show that the test will pass. I have the 6 tests, and all of them passing successfully. That's great, wonderful. Let's go to run the coverage to see if I have 100% coverage or not. Okay, running that, I'm using the coverage Python library, so it's saying that I have 100%, you see? 100% code coverage. Great. So at this moment, all of us, we are targeting to get 100% coverage, as Olivier said, but that doesn't necessarily mean that everything is good, and we don't have hidden cases, or edge cases are not covered by our test. So before using the MutePy, what I'm gonna do actually, I will create manually some modification in my code. For example, if I change, as just we have seen, for example, this one for the divide, I can put it 1. So I made one modification, which is constant. I didn't change operator. There are other types we said constant. Okay, and I save it. And I will run the test again. I don't need to run all the tests. I can just run the relevant test, which is for the divide. So the test passed, right? And then that means actually that the test didn't detect that I modified. And like I modified the code and the test passed. So there is a problem. And here we need the mutation testing. So I'm not going to do that. I will put it 0, and I will run the tool. So if I make this up, let me run the tool. So here, if you notice, this is the same command I just showed you earlier. I'm running inside Docker because this tool doesn't work in Mac, but it works in other operating systems, just to let you know. It doesn't work in Mac, so you need to run it inside the Docker image. So I'm going to run it and saying, okay, let me test my test. Okay, what happened here? I got a mutation score 64%. And what this tool did, created 14 modified copies of my original program by making one modification per each copy, as I just showed you, changing constant, changing operator, and run it against that test. And it seems that out of the 14, I have 9 got killed, which is perfect, but I have 5 survived, meaning that those modifications haven't been detected by my test suite. So let's see. Here it generates all that, gives you all the information. We can I replace the multiplication to exponential, the result will be the same, which is not good. Which means that there is a case hasn't been tested. So if I want to kill this one, I can do adding another statement by saying 2 multiply 4 multiply 3 equals 2x. And let me check if the test is good. Of course it's good. Let me run now the mutant. Remember, I'm trying to kill the case of the multiplication. So I'm going to run the mutant again, the function for the mutant. And as you can see here, actually the percentage gets increased higher instead of 64 to 71 because I managed to kill one mutant, which was the multiplication by adding extra test statement. So if you want to make sure that everything is good, I can look at it. It was the multiplication, which is here. This is the same exact function, and he is telling me that it has been killed. Okay, so that's great. And we need to do the same things for each surviving mutant. We need to kill them by adding extra tests, making sure what the test we are missing here. As I said that there is an HTML report can be generated, and it gives nicer presentation, visualization of your report if you don't want to look at it in the terminal. So you can see all the 14 mutants are listed here. You can go to each of them and check what has been changed, why it survived. Of course, it gives you more statistics about the duration of the test and so on. So basically, this is the idea behind the mutation. To test the test by creating a modified copy of your program and running your test suite against this modification. So if I go back to my application, I already fixed all those missing test cases, and if I want, I can rerun it again to make sure I'm gonna get. So for this application, because it's really simple, I managed to get 100% score. As you can see here, I got 100%. All the 14 mutants have been created, have been killed, which is great, and this means that my test suite is sufficient and is capable to detect bugs and hidden cases. So this is the first tool, and of course this has been modified, and you can see it's 100% the mutation score. This is the first tool, the MutePy. There are other tools. There is a mute. Also, the installation very straightforward. Pipe install mute, and you run the same commands. What I noticed for this tool, actually, it generates less number of mutants. So for this one, when I run it, it generates actually only 10, while the MutePy generated 14, which means that it covers more use cases. There is the last tool which I recommend that you use. Actually, I discovered it just last week. It's really the development there. The community is so active, and it seems that they are really developing many things, and it works perfectly for PyTest. If you don't use unit test for PyTest, so this tool is perfect. So you can use it, and the same thing. The installation is straightforward using Py, and you go through the commands. You run the Python script for that, and you pass your source code and your PyTest code as well. And I guess that's all for the Python, and we can move to the JavaScript.
Yes, let's move to JavaScript. The demo is going to be quite similar, actually. So this is my VS Code. So I have here the same thing. I have a calculator, which is very basic, doesn't even catch every possible issue, but I have a calculator here that does add, subtract, multiply, divide, modulo, square root, and etc. And I have my test suite here, where I have also one test per function. So I'm going to run it. So I can run the test. That would just run jest, and you can see that I don't have 100% test coverage, 100% of function coverage, but only 88% of lines have been tested. So you can still have a mutation test even though you don't have 100% test coverage. Just it will only test your test on this 88% coverage. And now I'm going to run Striker. I'm learning to type with one hand. Okay, nope. Okay. Okay, so what happened here? It's the same as with the Python tool, so you can see all the mutants that have been created here, and you can see all the ones that survived. So here they replaced less than 0 to less or equal to 0, less to 0 by false. And you can see that I have a mutation score of 77%. It killed 14 and 2 survived. And there's also an HTML report here, so I can click on it. Okay, let me. Here, so I have a report here, so that's my calculator. And you can see all the mutants that have been done. So 14 were killed, so you can even see them here. If I click on it, everything it did. But 2 survived. And the 2 that survived are here. So one, he did the less or equal. The other one, he did false. So I'm just going to go back to my code, and I'm going to add some tests. Okay, let's try divide by 0. I just run Striker again, and normally you will see that only one mutant survived. If I go back to my user interface here, the HTML report, you can see one survived, and it's when I do if false. So it means that there is also one thing that I'm not testing, and the one thing I'm not testing is the error. So I'm going to write a test where I divide by -1, I square root -1. That should throw an error. And now if I run Striker, you will see that the if false is now cached, and so all my tests have been killed. So this is a very easy way to know if all your tests, are efficient and if they manage to test all your code. Let me show you an example on a kind of bigger project. So this is a web application, very simple one. It's written in Angular. It doesn't do much, but it's still bigger. And if I run Striker, I know it's where is it? Test edition. You will see here that okay, it's running my test. It's creating a lot of mutants. You can see that there's 159 mutants that have been created. And you can see that my mutation score is like 57%. It's not much, especially since I run my test coverage here. We see that I have 100% test coverage. But still, I have 57% of mutation score. And if I go to the report here, you have even a bigger one. So this is the report, so you can see 57%. I can go to a component. You can go in a component and see all the mutants, not this one. Let's go to one, this is not 100%. You can see all the mutants that have been created that have survived, and then the same thing we did earlier, just see why it didn't work. So this one may be, this one, oh, as we showed in the slides, you just remove the entire content of the function. So this is a very interesting way to test your test. Just to show you about Striker a little bit, so Striker is a tool that works for JavaScript, TypeScript. There's also a Scala and .NET version of it. And depending on the language, you can see the kind of mutants you can create, because depending on the language, like I mentioned optional chaining that works on JavaScript, but it's not on .NET, for example. And so what is interesting is that even for all these kind of mutant, you can, in the, there is a config file, and you can define here everything you want. You can say the files you want to create the mutants. You can even say, I only want to create the mutants on Boolean, on statement, on logical operator. So you can configure everything in your config file and just run the mutant. And the same, you can say, I want the output in the console. I want the HTML one. They have even a SaaS version you can upload on their dashboard. You can have a JSON exit if you want to use it in your own dashboard and report. And so I encourage you to go see, and there's a lot of explanation on how all these work. And you can even integrate that very easily with your CI/CD. It works with Circle CI, GitLab CI, GitHub Actions. So pretty cool. Go back to the slides. Oh yeah, that's just how you install it, just npm package. I think very hard here.
All right. So we showed you two examples, two demos, one in JavaScript and one in Python. And we showed you, before running the mutation testing, we were having 100% code coverage, or Olivier has showed you less than 100% code coverage, and we were able to run mutation testing. So the mutation has nothing to do with the code coverage. Having code coverage, a high number of code coverage, 100%, is great. And I know that it's a magical moment of any developer in his life when you see 100%. Yes, I did it, so now my life is perfect, everything is great. However, we have seen that this is not enough. And this is not, it's good, but it's not enough. And that's why we need another metric, which what we call it the mutation score, where we know how much our test suite is sufficient. What we care about here is the quality of the test, not the quantity, beyond the line of code being executed during your test. So 100% code coverage is great, but we mentioned that sometimes you will not be able to get 100% mutation score. Of course, the higher is the best, but there are some situations you fix everything in your test. You added all the missing cases, the edge cases, the hidden cases, but still you will get stuck at 99. And you ask yourself, I will make it 100%. Actually, no, it's fine. It can be less than 100%. And the reason behind that is there are special kinds of mutants, what we call them equivalent mutants. What those equivalent mutants? So those, they make it change. Also, it's a modified copy of our original code, but actually it doesn't change the logic of the original code. What does that mean? Let's have a look at this example. So this example in Python, I want to fetch some web pages. So I pass URL, I get the web page. I want to do some optimization. So here, when I get the web page for the first time, I save it in a dictionary. I use the URL as a key, and I save it. Next time I get the same URL, I don't need to go to the server to fetch it. I have it located in my dictionary. So it's kind of optimization. Great, we all agree on that. Then a mutant of this code will be by removing the if statement completely, which means I removed the optimization. So we said that kind of a mutant, you can remove completely a statement, not always a changing operator or constant. I removed this one. So I created a mutant without this one. You run the test against this modification, the test will pass, which is normal. Because if I remove this if statement, when I get any URL, I will go to the server every time. I don't go to the cache. So removing this one, the test always will pass. What I removed, actually, I removed the optimization part. So I didn't really change the logic behind in the code, in the original code. And then you can't kill this mutant. So, and in this case, and there are similar cases to this one. Those what we call them equivalent mutants, so you can't kill them. And at this moment, you should accept that you will stuck at 99% mutation score. So you are good. So probably, I hope that you have seen with us that this tool is great. And yes, why not? We can improve the quality of our test suite, but still it has some limitations. The limitations that it can be time-consuming, and that's because there are hundreds, thousands of mutants can be created for your program, and that's why, thanks to all those tools, can make our life easier by automating, creating all those mutants for us and testing the test suite against them. And here, actually, you might ask yourself, itself a question, how can I apply mutation testing if you have, at scale, if you have what we showed you, there were like small example, calculator, and Olivier showed us another example a bit larger, but still, at scale, how can we run that? Actually, there is a study has been done by Google, practical mutation testing at scale, where they have like a code base composed of 2 billion lines of code, where they run 150 million of tests on daily basis. And they wanted to apply mutation testing against that. Can you imagine how many mutants can be created out of this 2 billion line of code? It's a huge. And running 150 million tests on daily basis, this is it's crazy. You can't do that, actually. So what they have done, actually, they propose an approach where they say we run a mutation testing against the new code at the level of the pull request. So incrementally, we run the mutation against the new code. We don't run it in the whole code base we have. Makes total sense. They say also that we should limit the number of mutants per each comment and per each pull request we create, which also makes total sense. And in the tools we showed you that Olivier mentioned that there is a configuration file where you say how many mutants or the percentage of mutant, what kind of mutant you want to test. So you can modify that, customize it the way you like. They also propose that we filter the irrelevant mutants or those equivalent mutants. So we don't need to see them, we don't need to generate them and run the test against them because they are equivalent, they don't add any extra value. In this way, they managed to run mutation testing against their code base. Last but not least, as we can see that you can't run a mutation testing and for black box testing because you need to modify the code. So it's only for white box testing. You need the original code to modify it. So you need that. We reached the end of our talk, and as takeaway, as we said, 100% code coverage, it's a great metric, and it's great to have, but it's not enough. And that's why we need mutation score. And what we care about behind all this, it's the quality of our test rather than the quantity. And why we care about that? Because the unit test or the testing, it's our primary source of truth to tell us if our code does what's supposed to do and it's meeting the standards. And that's why we want to improve the quality of our test suite. Automation is necessary because we have seen can be really time-consuming and overwhelming to the developers, and thanks to all those tools that it does that for us automatically. And last but not least, accept the fact you might not get 100% mutation score, and that's fine because what we have seen of equivalent mutant and so on. As we promised, so there are mutation tools for other programming languages. So it's not only for Python and JavaScript. So the most common and really widely used today for the Java is the PyTest. There is for C and C++, for PHP, for Swift, for Rust, and so on. So for Golang also. So whatever the language you like, just search for it, and you will find the mutation tool equivalent that test the unit or the test suite for your language. And I guess here's references we have used to prepare this talk. And I guess thank you very much. You can find our slides at theslides.com/myname. And of course, you can reach us to Olivier and me if you have any questions. And thank you very much for your attention. And what I hope with Olivier that you go back to your project, you try to apply it at your company, at your team, and just install the tool and run it against your test suite and see what you will get.
And what I hope is not mad at us, because there's always some people in the room that are like, I thought that 100% test coverage was enough, and then my tech lead is here, and tomorrow I have to make mutation test now. So don't be mad at us.
Yes, so try it. Thank you very much, everyone.
Thank you. Is there any question?
Thank you. It's not a question, but I think you just proved that test-driven development is the key, because when you apply TDD, your mutation testing will be 100%. Do you know why?
The thing is, so I'm going to repeat the question. So you are saying that TDD, it more or less has something to do with the mutation testing?
Yeah.
Well, actually, I would say not really, because in the TDD, you write your test before you start the development. However, in the mutation testing, you need the code, the original code. If you don't have the original code, you can't apply mutation testing.
What do you say that you don't need mutation tests if you do TDD? Doesn't mean you write all the possible tests when you do TDD, right?
Yes.
I think yes.
Well, I'm not 100% confident, because it's...
One example is for your the example about the cache.
Yeah.
You said that you cannot have 100%, but it's wrong, because if you have a conditional expression, the if cage, so you in TDD you wrote the behavior of that, so you expect that the server where you find the articles is not called. So you have a test for that.
I'm not sure. I haven't used that TDD, just to make sure. I haven't played with it, so I can't
okay,
be 100% sure.
We can talk about this after.
Absolutely.
Yeah.
Thank you.
Any other question? Yes.
Thanks. I wanted to ask you if you have less than 100% coverage, will it create mutation and not coverage code? No, it creates mutation only on coverage code?
No. It creates mutations everywhere, but it will run your test suite after, so it will only test. It tests your test basically. So if you change a part of your code that is not tested, when you run your test, if there is no link between the part that is tested and this one, it won't say it. Yeah, no.
It won't create a modified copy of a code, of the original code, if this hasn't been tested, because it will just generate for those that have been tested. So the idea is really focusing on the test. You will not be able to run it.
I have to check that.
It's only for the test you created.
Okay. And can you integrate mutation test in something like SonarQube?
Yes, this is a great question.
Yeah, I think there is a...
Yeah. Actually, there is a plugin which makes our life much easier even. So, Olivier mentioned
Striker works with SonarQube. In the documentation, there is a page on that.
Actually, I do have something. I'll go to the slide. Let me see. Here, actually, there is a plugin for SonarQube, and here this is the example for the PyTest, and will tell you what's the mutants, what has been killed. This is mutant. You see, those both they haven't been killed. So that's a great. Yes.
How magical the stat exists. Answer the question.
Yes. How you know? How you know that I have a slide?
Not the first one to ask the question. Good question.
Yeah.
Well, thank you very much, and enjoy the rest of the conference.